Quantitative analysis, determination of the salinity of water, is an important lab for a couple of reasons. As always, of course, I got my lab goggles on and my lab coat on, and I'm wearing gloves today, not so much because we're dealing with anything in the lab that's dangerous, but because we're being very quantitative. The numbers matter. And so I don't want to get my greasy little fingerprints on top of any of the stuff that I'm going to have to weigh out. And I'm going to use a very precise balance that weighs to the tenths of a milligram. And a fingerprint would register with that. So I'm going to be extra careful in terms of my contamination this week. So what we're going to check is how much salt is in water. You can check the internet and see how much salt is in regular ocean water, and then extra salty bodies of water like the Black Sea, I think it is extra salty, and compare it to these samples of water that our stockroom made up for us. So I'm going to do 4 of the samples for you. I'll post more data than just the 4, but I won't make you suffer through me doing more than 4. And the way we're going to do it is we're just going to add some water to some beakers that we know the precise mass of, and then heat the water off, evaporate the water off, and weigh the beaker once it returns to room temperature. There's a couple of important lab technique items this week. You can't weigh anything while it's hot, because once you put it in the balance, it can circulate the air inside the balance if the beaker is not at room temperature, either hotter or colder, and cause the balance to drift, which we don't want. The balance itself is very sensitive. Let me show you the balance. So this balance right here, is a Mettler Toledo, which they're one of the big companies that make it. And you can see on the screen that it reads to 4 decimal places, the tenths of a milligram, because this is the grams place, tenths of a gram, hundredths of a gram, thousandths of a gram, which would be milligrams, and then tenths of a milligram there. And on the back, it's got this little bubble which needs to be centered, because if the balance is literally not itself balanced, if it's not level, it won't work well. And you really shouldn't jostle these things or move them around too much, or damage them, because they're about a couple of grand a piece. And you pay for that extra decimal place versus the cheaper balances, excuse me, that for a couple $100 gets you maybe 2 decimal places. Try not to make you too dizzy. So what we're going to do first is to make sure that our water samples have chloride in them at all. Now, we don't really care whether it's sodium chloride or potassium chloride or gold chloride or anything. I mean, there's supposedly more gold in a cubic mile of seawater than has ever been dug up out of the ground. It's just there's so much other stuff in the seawater that nobody has figured out a cost-effective way of getting that gold out. So what we're going to do, we're not looking for the gold, we're just looking for anything chloride really, is we're going to do a very, very common test, which is to add some silver nitrate to our water sample. If you add silver ions to chloride ions, because silver chloride does not dissolve in water, you will get silver chloride solid, which is a white precipitate, a white solid developing. If you are testing for the presence of silver, you would add a solution of chloride to it, and again, you would get silver chloride that doesn't dissolve in water precipitating out. So what we're going to do is just add sample number 1 a little bit to test tube number 1. There we go. And we'll add sample number 2 to test tube number 2. My hot plate's not on, so I don't have to worry about melting my cap there. And we'll add, you can see where I'm going with this, sample number 3 to test tube number 3. Because if there's no chloride in it in the first place, there's no point in doing the experiment. And we'll add sample number 4 to test tube number 4. Good. Now we'll get our silver nitrate. And if we add a couple of drops, see if I can get the whole thing on the screen so you can see me actually adding it. Look at that. White precipitate. There's definitely chloride present because our silver precipitates out with it. I'll do it again. Sample number 2, test positive. Sample number 3, test positive. Sample number 4, test positive. And then all of the other samples I would also be positive as well. Because I made these samples, and well, the stocker made these samples, and I know that they will be positive for chloride. Now we'll weigh our empty beakers. We can't just hit the 0 button on the balance to set it to 0 because we're going to be weighing a bunch of other samples. Plus, we want to have the beaker's mass to subtract out later. We can't just set the balance on 0 with the beaker on it because when we come back later, somebody else might have used the balance. So we will weigh beaker number, I had these numbered properly. This is beaker number 4, beaker number 1, beaker number 3, and beaker number 2. We'll add them, we'll weigh them, and we will record the masses on our data sheet. So just to show you the process. Okay, I make sure that my screen is reading 0, which it is. You'll have to trust me. If it wasn't reading 0, I would hit the 0 button. I open the door on the balance, put in the beaker, close the door. Don't touch the table. This is very, very, very sensitive. I'll show you. If I just... So there's my value reading right now, 106.6712. If I lean on the table, well, this table is pretty sturdy because we just redid this lab. I'll hit the table. Okay, there you go. Hitting the table royally messes things up. And if you have a table that's not very secure, just touching the table can really alter your reading. So we don't touch the table, we let it equilibrate, and we record the mass of beaker number 1 on our data sheet. Or the mass of our beaker on the data sheet. You would record whatever the mass of the beaker is on your data sheet. Now, one way of doing this lab has you put a glass cover on top of the beaker, and so you would weigh the beaker with the cover. And the point of the cover is when the water is evaporating, sometimes it splatters out, and you don't want any of your salt splattering out. If the water splattered out without the salt, that wouldn't necessarily be a bad thing, but you can't let any of the salt splatter out. So sometimes you do this experiment with a cover on it, but then you need to know how much the cover weighs because you're going to weigh it at the end in case there's anything that did splatter onto it. You don't have to worry about it. But we're going to do it carefully without the covers on top of them. All right? So then I would weigh beaker number 2. Although I don't think you would do this multiple times with your sample. Just once would be good enough. So you're just weighing your beaker and putting your mass on your data sheet. I'll give you one set of data to record. All right. Okay. Then, next up, what do we got to do? We would take our sample, beaker number 1, bottle number 1. I've just done it that way so I don't lose track. And I'm going to put about 15 milliliters of water in there. About 15 milliliters. Now, am I measuring it in the graduated cylinder? No, because the exact amount doesn't matter. What does matter is that I go back to my balance and I weigh my water sample so that I can subtract out the beaker weight and figure out how much salt water is in there. I need the mass of my salt water because at the end I'm going to get the mass of salt that's left over, and the amount of salt out of the amount of salt water gives me my percent times 100%, gives me my percent of salt water. So back to the balance. Open the door, sample in, close the door, and get my reading. Then, onto the hot plate. I'll set my hot plate. Now, normally if I wanted to boil water, I would set the hot plate for around 300 degrees or so, to try and transfer at least 100 to it eventually. But this doesn't need to boil. So I'm going to set my sample, my hot plate today, on 200 degrees, and hopefully that won't splatter it out before it evaporates. All right? And then, just for the sake of argument, I'm going to do it with samples number 2, 3, and 4, so that I can get some more data and be able to post it for multiple people. I did not wash my beakers ahead of time because even if the beakers are dirty, so long as whatever contamination is on there doesn't boil away, it'll be in the beaker when I begin and it'll be in the beaker when I finish. If I had washed the beakers, I would have had to really, really carefully dry them, because any water that was on them when I weighed them at the beginning, when they were empty, would have burned away by the time the experiment was over. And that would absolutely mess with the results. And this is the kind of thing that you have to think about when you're doing your experiment. Because if you have water in the beginning when the beaker is empty and it burns away, then the amount of salt that's in there is going to appear to be less than what there really is. Because you had a little bit of extra, no, they're not. Yeah, it's gonna be less than it is, because we'll have had water on there plus the beaker at the beginning when the beaker was supposedly empty, and that water will have gone away. So the mass of your beaker empty was higher than it should have been. And so when you weigh the salt at the end, then that amount of water that was on the beaker, which you thought was beaker, is gone. And so it looks like more water disappeared than really did disappear, because the water that was on the beaker to begin with that disappeared didn't count, or at least you didn't account for it. So you have to think about procedural stuff like that when you're designing an experiment. And that's where the creativity, in addition to the science, comes in. So you can see, maybe, that there's a little bit of steam coming off of these guys. And that's all we're really looking for. Okay, give you a nice good close-up. Right, you can see the beakers are looking cloudy because the steam is fogging up the sides of them, and hopefully the camera can pick it up that we are steaming away our water. We don't need to boil it. If it snap, crackles, and pops, that's not going to be any good because we don't have a cover on there. The danger with having a cover on there is that if you put the cover on, then the water condenses on the cover, and it takes a lot longer to do the experiment. But we do have an experiment that we do in a different lab where you have to use the cover, because we're not just evaporating off water from water, we're evaporating water off of a solid, and that solid, some of the solids tend to snap, crackle, and pop, and if the solid flies out, again, you're altering your experiment in a way that you shouldn't have, because all of our salt needs to stay in the beaker. It can be on the sides, but it can't fly out. If it flies out, it's as if more water disappeared, and we don't want that. We only want our salt, our water to disappear, and not our salt. Because anything that disappears, we are assuming is water. So we'll let this go. I'll give you a good time lapse, and we'll pick it back up, and I'll show you the salt. We'll weigh the beakers at the end, and then that's the lab. literally watching water evaporate. There was an episode of Star Trek The Next Generation where Commander Data, who was always on the quest to become more human, turned off his internal clock to see if it felt like a different amount of time that it took water to boil if he was watching it versus not. To study the old saying, a watched pot never boils. And the episode ends with him being surprised that, in fact, his perception of time did vary when he could not measure it like a robot. Alright, so I gotta do this carefully so I don't burn myself and drop it. It's not too bad. If we look at this one, you can see that there's salt around the edges and there's not very much water left. Now, for safety reasons, you never heat anything to dryness because it can cause the glass to explode, shatter. So I think we're going to take this one off and just let the residual heat evaporate the rest of this water off. And if there's any residual water left on the sides of the beaker, then I'll put it back on carefully and briefly. But I believe that this one is done, and once it cools to room temperature, I could wait. I will put it on a piece of wire gauze so that very hot does not contact very cold of the bench and also shatter. Not seeing salt on the edges of the other ones. I also didn't measure my water volume, so there's not the same amount in each of these. This one's got some salt on the sides, a little bit. This one's getting there. Just FYI, I have these set to 250 degrees, the hot plates, and I'm not getting any boiling. Just because the surface of the hot plate is 250 degrees does not mean that all that heat is transferring 100% to the beaker. If you have a gas stove, your gas is burning at 800 degrees or something, and your water still takes a little bit of time to boil. Same principle. Heat transfer is not perfectly efficient. Just going to put this back on for a minute because it seems like it's cooling and leaving a lot of residual water. Definitely some salt floating around, precipitating out in this one now. If you were worried about burning yourself, you could use tongs to do this, but you gotta be really careful when you're working with tongs that you grab a hold of the beaker firmly and don't end up dropping the thing. So after about 45 minutes or so of heating and then putting it under a heat lamp for another 15 minutes or so, I've got beakers that have salt in them. This one broke apart enough for me to shake it around. Some of them are still pretty much stuck to the bottom, but if I broke it apart, you can see it's nice dry salt. So now all that's left to do is put it on the balance, record the mass of beaker plus salt, subtract out the weight of the beaker and or subtract that from the beaker and the water weight, and I'll have my salt weight. I suppose I could also just subtract out my beaker weight from what the beaker and salt is and get the salt weight directly that way. That's fine too. Then I got to compare my water weight before heating and my salt weight after heating, and that will give me my percent of salt in water. Won't make you sit through all of them, but at least one of them. Here we go. Balance on 0. Open the door. Salt in. Weight. Let it settle. Make sure the weight is consistent. If it's still going up or still going down slowly, that could be that water is still evaporating, or that I got it overly dry and it's still hot and water is condensing back onto it. Alternatively, if it's not at room temperature, the air inside there could be swirling around and messing up my weight, but my weight is consistent, so I record it on my data sheet in pen. No pencil for data recording, ever. It'll get you fired from a hospital. It'll get you fired if you're working in law enforcement and recording crime scene data. It'll get you fired if you're working as a pilot or any sort of FAA type of job. It'll get you fired if you work for the sanitation and you're writing down maintenance records. Everything has to be in pen so that it's not changeable, or it's obvious if it's been changed. And that's the whole point. You have to be neat on your data sheet. You make a mistake, you put one line through it so you can still see what the mistake was, and you write in your new data. So we'll record our mass of salt plus beaker, subtract out the beaker, we got our salt. We have our mass of water plus beaker, we subtract out the beaker, we got the water. Amount of salt divided by amount of water times 100% is percent of salt in water.